Today, I'm diving deep into the fascinating world of quantum chaos. It's where the wild and unpredictable meet the tiny and mysterious. Buckle up, because this is going to be a thrilling ride through the quantum and classical worlds. Quantum chaos is a branch of physics that tries to understand how chaotic systems in classical mechanics can be described using quantum theory. Sounds complicated? Let's simplify it. Classical mechanics deals with the large-scale, everyday world. Think of planets orbiting the sun or a ball rolling down a hill. Quantum mechanics, on the other hand, deals with the ultra-tiny world of atoms and subatomic particles. Now, here's the big question. How do these two worlds connect? According to the correspondence principle, classical mechanics is actually the large-scale limit of quantum mechanics. So, theoretically, if we zoom out far enough, the chaotic systems we see in classical mechanics should have quantum roots. But there's a catch. Quantum systems don't show exponential sensitivity to initial conditions like classical chaotic systems do. So, how does chaos emerge from something that isn't chaotic? This is where quantum chaos comes into play. Scientists have several approaches to tackle this puzzle. One method is developing new techniques to solve quantum problems where traditional methods fall short. When quantum numbers get large or the perturbations aren't small, new methods are needed. Another approach is correlating statistical descriptions of eigenvalues or energy levels with the classical behavior of the same system. Essentially, it's about connecting the dots between energy levels in the quantum world and the chaotic behavior we observe in the classical world. There's also the study of probability distributions of individual eigenstates. This includes fascinating concepts like quantum scars and quantum ergodicity, which describe how quantum states can be distributed in a chaotic manner. Then we have semi-classical methods, such as periodic orbit theory. This approach connects classical trajectories of a dynamical system with quantum features. Imagine tracing the path of a particle in a chaotic system and finding its quantum counterpart. Let's explore how this intriguing concept manifests across various branches of physics. Firstly, questions related to the correspondence principle arise in many different fields, ranging from nuclear to atomic, molecular, and solid-state physics, and even to acoustics, microwaves, and optics. This principle is crucial for connecting classical and quantum descriptions, but classical quantum correspondence in chaos theory isn't always straightforward. For instance, some versions of the classical butterfly effect don't have counterparts in quantum mechanics. In classical systems, tiny changes in initial conditions can lead to vastly different outcomes, but this isn't always the case in the quantum realm. Despite these challenges, important observations often associated with classically chaotic quantum systems include spectral-level repulsion, dynamical localization in time evolution, such as ionization rates of atoms, and enhanced stationary wave intensities in regions where classical dynamics only show unstable trajectories, like in scattering. In the semi-classical approach to quantum chaos, researchers identify phenomena in spectroscopy by analyzing statistical distributions of spectral lines and connecting spectral periodicities with classical orbits. Other phenomena emerge in the time evolution of a quantum system or its response to various types of external forces. Interestingly, in contexts like acoustics or microwaves, wave patterns are directly observable and exhibit irregular amplitude distributions. Quantum chaos in these areas often requires complex numerical techniques or approximation schemes to calculate properties, as simple and exact solutions are precluded by the intricate interactions within the system or the influence of temporally varying external forces. The quest to quantify spectral features of complex systems gave birth to statistical measures of quantum chaos. One such tool, random matrix theory, emerged from the need to characterize spectra of complex nuclei. This theory offers a remarkable insight. The statistical properties of many systems with unknown Hamiltonians can be predicted using random matrices of the appropriate symmetry class. Even for chaotic systems with known Hamiltonians, random matrix theory correctly predicts statistical properties of eigenvalues. This makes it an invaluable tool for characterizing spectra that would otherwise require extensive numerical efforts to compute. Various statistical measures are at our disposal to quantify spectral features in a straightforward manner. A key question in this field is whether there are universal statistical behaviors among classically chaotic systems. Interestingly, The statistical tests we use are indeed universal, at least for systems with few degrees of freedom. Berry and Tabor have argued for a Poisson distribution in cases of regular motion, while Husler and colleagues provide a semi-classical explanation for the Bohigas-Giannoni-Schmidt conjecture, which asserts the universality of spectral fluctuations in chaotic dynamics. One widely used measure, the nearest neighbor distribution of energy levels, is relatively simple to interpret and has become a cornerstone in describing quantum chaos. By understanding these statistical descriptions, we can better grasp how quantum mechanics and classical behavior intersect. As we continue our journey through the intricate world of quantum chaos, we now turn our attention to recent directions in this fascinating field. One open question that remains is understanding quantum chaos in systems with finite-dimensional local Hilbert spaces, where standard semi-classical limits do not apply. Recent works have allowed for analytical studies of such quantum many-body systems, opening new avenues for exploration. Traditionally, quantum chaos research has focused on spectral statistics, both universal and non-universal features, and on the study of eigenfunctions of various chaotic Hamiltonians. Before the phenomenon of quantum scars was reported, it was conjectured that eigenstates of a classically chaotic system would fill the available phase space evenly, up to random fluctuations in energy conservation, a concept known as quantum ergodicity. However, quantum scars defy this expectation. In a quantum eigenstate of a classically chaotic system, the probability density can be enhanced in the neighborhood of a periodic orbit, creating scars that are above the statistically expected density. These scars offer a striking visual example of classical quantum correspondence, even away from the usual classical limit. They also serve as a compelling example of quantum suppression of chaos. For instance, in quantum dots perturbed by local potential bumps or impurities, some eigenstates become strongly scarred along the periodic orbits of their unperturbed classical counterparts. This phenomenon is known as perturbation-induced quantum scarring. Further studies in this field concern the parametric dependence of the Hamiltonian, as reflected in the statistics of avoided crossings and the associated mixing seen in the local density of states, LDOS. There is also a vast literature on wave packet dynamics, including the study of fluctuations, recurrences, and quantum irreversibility issues. Special attention is given to the dynamics of quantized maps, with the standard map and the kicked rotator considered prototype problems in this area. These systems continue to provide valuable insights into the complex interplay between classical chaos and quantum mechanics. As we uncover these recent directions in quantum chaos research, we gain a deeper understanding of the underlying principles that govern chaotic systems. Thank you for joining us in this exploration.